All right, welcome back. So continuing our work with polar functions, we're going to take a look at polar forms of equations, the idea of converting between polar and rectangular. So we know from our graphing and plotting polar coordinate points, our coordinate point is r comma theta, radius and angle, and then obviously a rectangular coordinate point is x and y, something you've been working with most of your academic career. So the way we can convert between the polar to the rectangular is recognizing the r cosine theta is equal to the x value, whereas r sine theta is equal to the y value. So if we're given this polar coordinate right here, we know that this is r and this is theta. So x is going to be negative 4 cosine of negative 11 pi over 6, which we could recognize as a coterminal angle, means x is equal to negative 4 cosine of positive pi over 6. We add 2 pi to that. Cosine of pi over 6 is going to be root 3 over 2. And negative 4 times root 3 over 2 is a negative 2 root 3. The y coordinate would then be negative 4 sine of theta. So I'd worked with a coterminal angle with the first one, so the other option is when it's a negative angle, is remember your negative angle identities, where I can pull the negative out from the sine. This becomes positive 4 sine of 11 pi over 6, which would be a negative 1/2. So we get negative 2 for y, so this into rectangular form is negative 2 root 3, comma negative 2. So again, you're welcome to use your negative angle identities. Just remember that sine of negative theta is negative sine theta, whereas cosine of negative theta would just be cosine of theta. The negative angle for cosine just cancels out because it's an even function. All right. So if we want to go from rectangular to polar, we need to use the x and y points to find r and theta. So r is equal to the square root of x squared plus y squared. Theta is tangent inverse of y over x, but if x is negative, we do need to add pi to that tangent inverse of y over x. If y is negative, it doesn't matter. We just do our inverse function, that's it. It's only when x is negative that we have to consider doing a plus pi at the end of that. So we have 2 comma 2 root 3, so that's our x and y. So our r would be the square root of 2 squared plus 2 root 3 squared, which will get us 4 plus 12, square root of 16, which is 4. And as for theta, theta is the tangent inverse of y over x. Since x is positive, we are not going to add on pi there. So we'd have tangent inverse of root 3. And the tangent inverse of root 3 is going to give us pi over 3. So this coordinate point would be at 4 comma pi over 3. If we had a slightly different coordinate point, let's use the same numbers, but let's say it was negative 2 comma 2 root 3. Obviously r still works out to be a 4, but now theta would be tangent inverse of 2 root 3 over negative 2 plus pi. Because since x is negative, we need to add the pi onto the answer there. So we have tangent inverse of a negative root 3, which is negative pi over 3, plus pi gets us 2 pi over 3. So this would be equivalent to 4 comma 2 pi over 3. And then if I was dealing with positive 2, negative 2 root 3, because the x is negative, x is positive, we're not going to add on pi. So this would be tangent inverse of negative 2 root 3 over 2, which is our tangent inverse of negative root 3, which is negative pi over 3. And we wouldn't have to add on pi to that because the x value is not negative. So this coordinate point would be 4 comma negative pi over 3. Or you might find sometimes the MCQ would show this as 4 comma 5 pi over 3 to account for a coterminal angle there. All right, so you just have to kind of watch out when there's negatives involved with the coordinate points. X is negative, you add on pi to the theta equation. Y is negative, we don't care. We just solve it out and see what happens. Now, when it comes to rewriting equations, you'll be doing your conversion between rectangular and polar in the equation format using pretty much the same kind of stuff we just did there. And the reason why we want to do this kind of thing is because there's sometimes where rectangular works out better, sometimes polar works out better. This first example here, x squared plus y squared equals 9, is a circle. of radius 3 centered at 0, 0, but the polar equation r equals 3 is the exact same thing. As you can see, that's clearly a much simpler equation. R equals 3 is much easier than x squared plus y squared equals 9. Whereas the linear equation, 2x minus 3y equals 6, is equivalent to r equals 6 over 2 cosine theta minus 3 sine theta. Obviously, the polar form of that linear line is much more complicated. So it really just kind of depends on the type of equation, which one is going to be easier to work with. For right now, obviously, you're going to work with what I tell you to work with, but in future courses, you get to make a choice. So going from rectangular to polar, the idea is you're replacing the x and y with r cosine theta and r sine theta, and just kind of simplifying the resulting equation using your algebra skills. So I don't really like fractions, so I'm actually going to rewrite this as 4y equals x, which means this is 4r sine theta equals r cosine theta. And while r is a variable, it is never going to equal 0. If it did, then we wouldn't really have any actual equation. So you're always going to divide by r each and every time you solve these problems. And in fact, to isolate the trig function, I'm going to divide by r sine theta. Leave that 4 alone on the left side. R is cancel. Cosine over sine is cotangent. If we had left the 4 on the right-hand side, we divide r cosine theta over, you would find you'd have 1/4 equals tangent theta for your answer. So it just kind of depends on which one you were looking at. Now, let's say, for example, we did all that and we got this situation here. We got tangent theta equals 1 after we're done solving that. You should then go further and say that means theta equals pi over 4 and say that is the appropriate polar form of that particular answer. So obviously 4 or 1/4 doesn't show up on the unit circle, so we can't go further with that. But if it does give you a unit circle value, 1, √3, √3 over 3, stuff like that, you should put it into its theta form rather than a tangent theta format. All right, now here we have our equation of the circle. We have x plus y squared, y minus 3 squared equals 10. What we're going to do is we're going to actually FOIL this out. X squared plus 2x plus 1, y squared minus 6y plus 9. And then we're going to group the x squareds and y squareds together. And we're going to kind of like, I guess, group the x terms, y terms together. You'll find the 1 and the 9 become a 10 and cancel the 10 on the right side. And the reason why we're doing this is because this part right here is equivalent to r squared. And again, the individual x's become 2r cosine theta. The individual y becomes r sine theta. And for most of these questions, the goal is to get r completely by itself. So we'll notice that every single term has an r in it. So if we divide everything by r, we get r plus 2 cosine theta minus 6 sine theta, which means r is equal to 6 sine theta minus 2 cosine theta. So for the vast majority of these questions, your goal really is going to be dividing by r at some point in the problem once you get everything rearranged. And then isolating the r expression from there. So in this parabola format, again, we really don't like the fraction, so I'm going to make this 3x equals y squared. And once again, we're going to rewrite the x and the y as r cosine r sine. So 3r cosine theta. This would becomes r squared sine squared theta. If we're trying to isolate r, it looks like the right-hand side is the best bet, because if we divide both sides by r sine squared, we cancel sine squared from the right side. R squared over r just becomes an r on the right side. The left side r also cancels, and we're left with 3 cosine theta over sine squared. Now, can't leave it like that. We want to try and simplify this a little bit more, and this is where the Unit 7, our trig identities come into play a little bit. We can rewrite this as 3 cosine theta over sine theta times 1 over sine theta, because that becomes 3 cotangent theta times cosecant theta. And now it's in a simpler format. But again, r is isolated, and that's the whole goal for each of these questions. So those are some examples of going rectangular to polar, dealing with a circle, parabola, linear line. That's the basic premise behind what we can do with that. Other questions in the same kind of style, you again do what we kind of did there. get the x and y's to replace and kind of start rearranging and ultimately divide by r's more often than not. Polar to rectangular, same kind of idea. It's not sometimes as straightforward. You're going to try and look for r sine thetas to become y's, r cosine thetas to become x's, the x squared plus y squared to become, to replace the r squared you see in a problem. Stuff like that is generally the goal. Alright, so we have tangent theta equal to 2. So if you're given tangent to start off with, that's just simply y divided by x. Where we can multiply the x over and get our linear equation y equals 2x. Pretty simple. If we were given theta rather than tangent theta, let's say we're told theta is equal to pi over 6, we're going to use tangent theta equals, again, y over x, but this time we're going to use the pi over 6 as an actual theta value that they give us, because we know that's root 3 over 3 equal to y over x, and we multiply the x term over to get rid of the fraction, we get our linear equation y equals root 3 over 3 times x. So it really just kind of depends on which one they give you. If they give you tangent to start, replace it as y over x. If they give you theta to start with, you're going to plug that into the tangent theta equation and approach it that way. Now if we're given r equals a number times a trig function right here, the idea is this kind of came from us dividing the r away from the problem, so we're going to kind of reverse that process. We're going to multiply both sides by r. Because we want to create r squared and we want to get an r sine theta in the problem. And I can't get r sine theta by squaring both sides. That only gives me r squared. But now by having an r squared, it's x squared plus y squared, whereas the r sine theta is y. So I can move that back over, get x squared plus y squared plus 6y, and then I'm going to complete the square, where I'm going to fill in that missing blank there is a 9, because half of 6 is 3 and 3 squared is 9, which I then fill in on the right-hand side. That gives me the equation of my circle, x squared plus y plus 3 squared equal to 9. Alright, so you have r equals some number with a trig function, sine, cosine, sine and cosine. Just multiply both sides by r to create the r squared and to create the r sine, r cosine theta in the problem itself. Now, if we have the cotangent cosecant, you can recognize this. That came from that parabola situation, where we are going to ultimately multiply both sides by an r, but first we're going to rewrite this as 5 cosine theta over sine theta times 1 over sine theta. Because if I multiply both sine thetas over to the other side to get rid of the fractions, I get r sine squared equal to 5 cosine theta. Now multiply by r, I get r squared sine squared equals 5r cosine theta, where we can recognize this is r sine theta expression being squared, which gives us a y squared equal to 5x, and then we divide the 5 over, get 1/5 y squared equal to x. And again, these are just simply a couple examples of going through our polar into rectangular format. This kind of process this is how you want to solve out these questions. All right, we got a couple videos still left for Unit 10, so I'll see you guys next time for those videos.